Okay, in this video we're going to look at how to determine an electric field at a point. Here's our point X up here. And for this example we're going to deal with a situation where we have two-dimensional contributions, so we're going to have to deal with vectors as we do this problem. There's nothing particularly challenging about this problem, it's just going to be a little bit long and have a lot of steps. Then we're going to determine what force would act on a point or a particular charge at that point, so 2UC or negative 4UC. And while we're doing that, hopefully we'll illustrate why when we're determining what an electric field is, we always use a positive test charge. So once again, to determine the electric field, we're going to assume that we have a positive charge up here. And then we're going to determine the electric field from object 1 and from object 2. And then we'll take the vector sum of those to come up with the total electric field at that point X. So first things first, we've got to do the geometry here. We've got to figure out what the separation distance between these charges and the actual point of interest is, and we also have to determine the angle. So first things first, to determine the separation distance, we're going to use Pythagorean theorem. Hypotenuse squared is equal to a squared plus b squared. So here, oops, let me try that again. The hypotenuse is going to be equal to the square root of 18 squared plus 8 squared. I wonder if I made this a little bit bigger, if that'd be a little bit. My pen seems to be dragging a little bit as I'm writing, so I'm just going to see if I can clean that up. 18 squared plus 8 squared. There we go. So 18 squared plus 8 squared, square root the total. So I got 19.7 centimeters for this separation distance. And I've got to get this one. So 8 squared plus 15 squared. We'll take the square root of that, and that'll get me the hypotenuse. So 8 squared plus 15 squared, square root that. I got 17. So this one is 17 centimeters. Remember, when I put those into the formula, I'm going to convert them to meters. I also need these angles. I might as well do that while I'm here. So I'll call this one theta and this one alpha. So tan theta is equal to 8 over 18. So I can use that to get theta. So I get 24 degrees, essentially. So that's 24 degrees. And alpha, tan alpha is equal to 8 over 15. So alpha is going to be 28. So 24 and 28 degrees. So that one's 28 degrees. All right, that's all the geometry I have to do to help me figure out what direction and what magnitude my electric fields are going to be. Now I'm going to use the electric field formula to determine the electric field at point X. I'm going to do each charge separately, so I'll do E1, which will be KQ1 over R squared, or 9 times 10 to the 9. I'm getting a lot of trails on my numbers here. I don't know why. I'm going to keep going, but we'll keep an eye on that. The charge there is 4 microcoulombs. So 4 micro means times 10 to the negative 6. Divided by that separation distance. Remember, when I do that separation distance, I have to put it into meters. So 19.7 centimeters is 0.197 meters squared. So the magnitude of the electric field generated from point 1 is, I'm going to do this in scientific notation, 9.3 times 10 to the 10 to the 5 newtons per coulomb, or amount of force per unit charge. And E2, same formula here, E2 equals KQ over R squared, which is 9 times 10 to the 9. Q is 2 times 10 to the negative 6. You'll notice here, once again, I'm neglecting the charge, or the sign on that charge, as I'm going to consider directions separately later. So I don't need that sign to get me the correct sign on this. I'm just going to deal with that later. So 9 times 10 to the 9 times 2 times 10 to the negative 6 divided by 0.17 squared. So here I have 6.2 times 10, 1, 2, 3, 4, 5, to the 5 newtons per coulomb. And again, you'll notice I've just done the magnitudes of these. I've left the directions off, or I've left them blank. Now, to get this direction, I'm going to erase all this so that I can write down here. If I'm considering the electric field generated from point 1, you'll notice that I have a positive charge generating that electric field, and I assume a positive test charge, so like charges repel, so I'm going to repel upwards this way, or up and away. So that force is going to be up and away at an angle of 24 degrees, and that is going to be 9.3 times 10 to the 5. And this one is negative, and I have my positive test charge, so that's going to attract, unlike charges attract that object in. So for my secondary force here, I'm going to be coming in. The angle where I started was 28 degrees, and I have 6.2 times 10 to the 5 newtons per coulomb. So those are the two vectors that represent my electric field generated by charge 1 and charge 2. Now I have to take the vector sum of them to come up with the total electric field. Expand this here, give myself a little bit more space to work with. So this component will be 9.3 times 10 to the 5 cos 24, as it's on the cos side. And that works out to be 8.5 times 10 to the 5. This one will be the sine. So this would be 9.3 times 10 to the 5 sine 25. So here I have 3.9 times 10 to the 5. This guy, I haven't left myself enough space here, so I'll do it up here, is 6.2 times 10 to the 5. And that's on the opposite side, so that's going to be the sine of 28. So I have 2.9 times 10 to the 5 for that component. And when I put that into my chart, I'm going to make sure I include him as a negative because he's going in the negative y direction, but I won't do that right now. And here I have 6.2 times 10 to the 5, and this is the cos for 28. And that's 5.5 times 10 to the 5. So we have all our components. Now all we have to do is add our individual components to come up with our total electric fields. So I don't know what I'm doing here, hold on. I'm going to deal with my x direction and my y direction separately. I have my electric field from point 1, I have my electric field from point 2. So in the x direction, I have 8.5 times 10 to the 5. And in the y direction, I have 5.5 times, oh no, sorry, I'm copying the wrong component here. I'm looking for this guy right here. So 3.9 times 10 to the 5. And then in the x direction for the other one, I'm still going to the right, so that's positive 5.5 times 10 to the 5, so those guys will add together. And here I can see that I'm going down, so this is going to be negative 2.9 times 10 to the 5. So I can recognize that the electric field total is equal to the sum of the individual electric fields. So 8.5 plus 5.5, it's 14, so this is going to be 1.4 times 10 to the 5. And 3.9 less 2.9 is going to be 1.0 times 10 to the 5 in the y direction. So now I simply have to recombine those vectors. Hold on, this should have been times 10 to the 6. That's times 10 to the 6, right? Yeah. So 1.4 times 10 to the 6 and 1.0 times 10 to the 5. .4 So if I go 1.4 times 10 to the 6 squared plus 1.0 times 10 to the 5 squared, taking the square root to find the long side here, I get 1.4 times 10 to the 6. So that 1 times 10 to the 5 wasn't big enough to make any difference, but it will affect my angle, x, positive y. So what's the angle here? I'm going to use tan. So I get 4 degrees. Theta is 4 degrees. So x, 4 degrees, y. So that's my total electric field. So it's a lot of work to get there, but I don't think any one of those individual jobs or any one of those individual points was challenging. Now, let's talk about how we can use that to make future calculations simpler. So that's kind of a pain, so why would we do it? Well, let's imagine a scenario where we're going to have a common setup like this, and we're constantly going to be dealing with electric forces of particles at position x, and we want to be able to predict what is going to be there easily. Now that we've determined this total electric field, 1.4 times 10 to the 6 newtons per coulomb, x, 4 degrees, y. That's what it was, wasn't it? Yeah, that's what it was right there. Okay. How can I determine the electric forces? Well, it becomes very easy. So let's determine the electric force if a 2 microcoulomb charge is put at that place. Just like we did with the force of gravity, where we made little g, or the gravitational field strength of Earth, now that we have the electric field, we can simply multiply by that by the charge to get the overall force acting on the particle. So if I have 1.4 times 10 to the 6 newtons per coulomb, x, 4 degrees, y, and I multiply that by my charge of 2 times 10 to the negative 6 coulombs, then I can come up with my new force, or my actual force, which will be 2.8 newtons, x, 4 degrees, y. And that's pretty easy. So we can imagine if we did all of the big work to get this, how we could put a large variety of different charges at point x and predict what the resulting force would be on those charges. So that's half of what I want to illustrate here. The other half is, if you'll recall, way back at the beginning I say we're going to use a positive test charge to determine this electric field. Let's see what happens with this equation when instead of putting in a positive value, we put in a negative value. So here, our electric field was designed for a positive charge, so a positive charge would be directed along x 4 degrees y. Let's see what happens if we put in this negative 4 microcoulomb charge. So negative 4 times 10 to the negative 6 coulombs. Well, you'll see the negative sign multiplies by the positive sign over here, and I get negative 1.4. Oh, not 1.4, sorry. 5.6 newtons of charge x 4 degrees y. And so this negative means that I'm going in the opposite direction to this x 4 degrees y, which makes sense, because if a positive charge was going to be pushed on x 4 degrees y, a negative charge would be pushed in the opposite direction, negative x 4 degrees y. So by using a positive test charge, when I multiply by this, it predicts the direction correctly, and whether it's positive or negative. If I put a positive in, and this is positive, then the two signs work together, and this is positive, and the direction remains unchanged. If I put a negative in, then I go a positive times a negative, and this becomes a negative, and the direction becomes reversed, which would be appropriate for a negative charge. So by using a positive test charge, we effectively also predict the force that would be applied on a negative test charge. We just have to keep the negative when we go ahead and use this formula, so then that way we get the opposite direction from the positive charge. So that's why we use a positive test charge in electric fields. So if you have a more complex situation, this is two-dimensional. You could even do this with many charges, although obviously it would get it would become a lot of work, but maybe a good thing that a computer can do. You can predict the electric field from each charge individually, and then the total electric field will be the sum of those. Of course, it's a vector sum because electric field is a vector. And once we get the electric field, that's really useful, because what it allows us to do is easily predict the resulting force if we know what charge that electric field is acting on.